Welcome everyone to section number 9. This is the final section in chapter 2. We're going to be talking about linear approximations and differentials. So in this video we're going to go over some of those concepts, we're going to give you the definitions, and then we're going to see how these actually arise out of pretty natural questions. And this is really our desire to approximate things and not make our lives too horrible. Alright. So here's the problem that I want us to consider. Right, we're trying to approximate the square root of 4.5. And so we know some things, right? The square root of 4 is equal to 2. So like 4.5, maybe it's 2.1, maybe it's 2.2, but right, these are hunches, right? And the claim is that there's a way to use calculus to actually give us a good approximation with actually quite a bit of accuracy. So the idea here is that we're going to use the tangent line. So I went ahead and I gave us our function, right, the square root of x. And again, we would like to approximate the square root of 4.5, and kind of we're interested in the tangent line at a nearby point, in this case at 4. So if I went ahead and I graphed maybe my tangent line, I'm going to give us the idea here. So here's the point at 4. And I'm going to go ahead and graph my tangent line, maybe in purple or something like this. I'm going to do my best to give us a nice straight line that's tangent here. I did an okay job. Okay. Something like this. The tangent line, again, remember we're trying to get the square root of 4.5. The square root of 4.5, well, here's the square root function. And so the height here at 4.5, well, that would be the square root of 4.5. And one thing that you might notice is that this tangent line's height at 4.5 right here is very, very close to it, right? They almost have the same heights. And so if I can figure out the height of the tangent line at 4.5, then the claim is this is actually a pretty good approximation to the actual function's value at 4.5. In this case, the square root of 4.5. So let's go ahead and do this out. Let's find the tangent line equation and then use that to approximate the square root of 4.5. All right, so I have some work to do. So tangent line equation. Well, okay, maybe first thing I want is the function's value at 4, right? Because this is the tangent line at 4. So f of 4, well, that's the square root of 4, and that's equal to 2. And then the other thing that I need for my tangent line is, right, the derivative at 4. So let's go ahead and calculate out f prime of x. Remember, this is x to the 1/2 power, right? X to the 1/2 power. So I'm going to use the power rule. The 1/2 comes down, and I get x to the negative 1/2 power. And we've probably done this so many times now that maybe you're just already writing 1 over 2 root x, right? So there's the 1/2, and then when you have the negative exponent, right, that's the same thing as putting it in the denominator, and then again the 1/2 power is the same thing as the square root. Okay, so now I can figure out the derivative at 4. That's going to be 1 over 2 root 4. Well, root 4 is again 2, so I'm going to have 1 over 2 times 2. That's going to be 1/4. Okay, so again, I want a tangent line equation. Remember, this goes y minus some y point, right? So here's my f of 4 in this case. So that's the y value, is equal to slope. So in this case, what we have 1/4 times x minus the x value. And again, the x value is 4 in this case. So here is my nice tangent line equation. Let's go ahead and rearrange this a little bit. I'm going to solve 1/4 x minus 1. And then let me go ahead and add 2 to both sides. So I get y is equal to 1/4 x plus 1. Okay, and well, again, the claim is if I want to know the actual function's height at 4.5, in this case the square root of 4.5, well, if you figure out the tangent line's height at 4.5, the claim is these are very, very close to each other, right? This is a good approximation. So let's figure out the tangent line's height, aka its y value, at 4.5, aka when x is 4.5. So okay, let's go ahead and plug in 4.5 everywhere I see an x. Now, 4.5, right? This is a little bit messy. I'd probably actually like to use, like a fraction. So instead of 4.5, Remember, 4.5 is the same thing as 9/2, right? 9/2 is the same thing as 4.5. So let me go ahead and plug in 9/2. So this would give me that y is equal to 1/4 times 9/2, or 4.5, plus 1, and I just find it's a little bit easier to manipulate with fractions rather than decimals. Okay, so this is going to be 9/8, right, because you just multiply across, plus 1. 1 is, of course, the same thing as 8/8, right? So this is the same thing as 17/8. And that would be my final answer. However, sometimes you want to think about, actually, what is this closer to? So, right, 16/8 would be 2. So this would be 2 and 1/8 if you'd like to write this as a mixed number. And if you have a calculator, or if you just really are good friends with your eighths, right, this is 2.125. Right, so here's some different ways that you can represent this. Again, in this class, you're mostly going to be using, right, this like 17/8. So again, we know that it was supposed to be close to 2, and right, my guesses were 2.1 or 2.2, and according to this tangent line approximation, well, 2.125 would actually be a good approximation for the square root of 4.5. So again, before we start writing down some of our definitions that I have down below here, let me go through this one more time with our Desmos graph here. So I already have the square root. This is the red line right here. And I graphed very nice our tangent line. So our tangent line is the blue one here at 4. And our goal again was to figure out the height of this function, the square root function at 4.5. And the claim is, if you look, this blue line, the tangent line, is actually very close to the function, right? This red line around 4.5. So if I go ahead and zoom in, for instance, you can see, of course, at this point, at 4, they're exactly equal to each other. That's one of the aspects of, right, the tangent line, is that it should actually contain this point. So at 4.5, you can see, even as I zoom in, these are very, very close to each other. Their heights are only off by a little bit. So again, the tangent line does a good job of approximating the function, again, so long as you're kind of somewhat nearby, right? So 4.5 was pretty close to 4, so you can see that actually it does a pretty good job. As you move farther away, you can see the tangent line does kind of a worse and worse job, right? If you go over here, for instance, if you went even farther, right, this blue line and the red line, they start to really separate. But at least for a while, the tangent line and the function are close to each other. All right, so let's put this down into some actual more formal definitions and stuff, so that way we can talk about it. So the first thing is a nice remark here. So linear approximation, right? So that's one of the names in the title there. So linear approximation and differentials. We'll get to differentials in a second. But linear approximation, or sometimes it's called tangent line approximation, are two names for using the equation of the tangent line to approximate a function. So the definition here is that, so L of x is equal to f of a plus f prime of a times x minus a is called the linearization of the function at a. And the claim is this is just exactly the tangent line, except for that it's solved for y, right? So basically this y value up here, we just solved for y, and we called this a function in its own right. So we called this L of x, the linearization, or the line that goes through this point f of a and has the slope that's the derivative. So again, this is just the tangent line. It's just kind of given a new name. It's called the linearization. And again, what I said kind of earlier is that the function's height is approximately equal to the tangent line's height, or the linearization's height, so long as x is close to a. So again, so long 4.5 and 4, those are relatively close numbers, and you saw that the tangent line's height and the function's value's height, right, they were pretty close to each other. They were only off by a little bit. All right, so that is the idea behind linearization, right, or linear approximation, that we can use the tangent line to approximate the function. Sort of a dual topic, right, to linearization is an idea called differentials. Differentials, again, they're closely related to linearization, but they answer a slightly different question. That question being, if a graph, y equals f of x, is originally at x equals a, how much does the y value change if your x value moves a little, right? So the small movement in x is sometimes called delta x or dx. So a small movement in x, and the question is, how much does your y value change? So kind of an equivalent question almost, again talking about differentials, use a differential to approximate how much does the value of y equals square root of x change as x moves from 4 to 4.5. All right, and before we actually solve this, let me go ahead and note that I have a nice Desmos app here. So if you go to this, and claim as I have it already open, so this was the linearization one, and here's the one that links to the differentials. So I'd like to just visualize these differentials first before I try to solve for one. Okay, so here I am at 4. Let me zoom way in. Again, I have the same function, the square root of x. It's pinned here at a equals 4. That's my tangent line. It's going through at this value 4. And I'm moving a little bit to the right. I'm moving 0.5 to the right. So that's going to end up at 4.5. Okay. And again, the question that I'm asking now, the claim is differentials will solve, is how much does the y value change? So here's the y value originally at 4. And if you move over to 4.5, how much does it increase? Well, you can see that the actual function goes up, well, this length of the red line here, right? It goes up this much. This red line's worth, that goes to the square root of x. Now, we can use this tangent line idea to answer this question as well. So again, this blue line right here, now it doesn't go all the way down to the x-axis, right? So we're not talking about the overall height, but we're talking about the change in height, right? So in this case, the red line represents how much the function actually changes as you move from 4 to 4.5. And then the blue line here, this blue dashed line, represents how much the tangent line changes as you move from x equals 4 to x equals 4.5. And you can see again that they are very, very close to one another. So if you can figure out how much the tangent line changes, the claim is this is a good approximation for how much the actual function changes. All right, so with that in mind, let's go ahead and try to calculate this out. And again, all those words I was saying just mean, again, we're going to take the tangent line's height, tangent line height, at 4.5, so at x equals 4.5, and I'm going to subtract away the tangent line's height at 4. And then that should give me the approximate change in the function. Well, in this case, we already did a lot of this work, right? We figured out the tangent line's height at 4.5. It's this 17/8. So, okay, I'm going to do 17/8. And then I'm going to subtract away the tangent line's height at 4. Well, at 4, the tangent line goes through 2, right? Because it's a tangent line to the function at 4, right? And again, you could just plug this in. If you plug in 4 into your tangent line equation, you're going to have 1/4 times 4, and that's going to be 1, plus another 1, that equals 2. All right, so let's go ahead and subtract away 2. Well, 2 is the same thing as 16/8, and so we're going to get the answer of 1/8. Or again, if you'd like, this is equal to, there we go, 0.125. So the claim is the change in the function's height is approximately equal to 1/8, or 0.125. More formally, if I wanted to use this whole linearization, right, so I have the linearization, which is the equation of the tangent line, and this was equal to, well, in this case I pinned it at x equals 4, right, so my a value is 4, so this would be f of 4 plus f prime of 4 times x minus 4. So there's my tangent line equation, aka the linearization of my function at 4. And this gave out the height right here. Let's go ahead and subtract away the function's value at 4. So this is going to be L of x minus f of 4. And that's going to be equal to f prime of 4 times x minus 4. And now you can see this is actually the change in height, especially if I plug in 4.5 for my x. 4.5 f prime of 4 times 4.5 minus 4. So again, this is how much did our y value change, right? Here it was originally f of 4, and then here's the height at 4.5, or really the tangent line's height at 4.5. And the claim is this is equal to f prime of 4 times 4.5 minus 4. And let's just verify that we get the same result. So again, we already calculated out f prime of 4. That was 1/4. And now this is, 4.5 minus 4, that's going to be 1/2. And so we get the same answer of 1/8. So again, differentials, they're very closely related because we're still using the tangent line, but now instead of asking what is the height, we ask how much did the height change. All right, and let's go ahead and write down then some more formal notation, right, for differentials. And for differentials, we denote these things with dy. So again, this is the change in the height of the tangent line. So that's our dy value, and this is equal to f prime of a, so again, wherever you're pinning that tangent line to at some a value, times dx, where again, dx is a small change in x, but this is a variable. So in this case, up here, our dx, right, would have been 0.5, right? We changed from 4 to 4.5. So again, our dx would be 0.5 in this case. Here's some more definitions, right? So dx, or this change in x, well, this is the difference between x and a, and this is also denoted as delta x. So these things mean the same thing. However, when you're talking about delta y, right, so in this case dy is up here, delta y is something different. This is the actual change in the function's value. So again, this delta y, if I go back here, the delta y is this red line right here. It's the actual change in the function's value. And then we use the tangent line, right, this blue line right here, this is our dy. So this one would be our dy, the blue line, and our delta y would be the red line. And again, the claim is that these are close, but they're not necessarily equal to each other. So let me go ahead and specify this is the red line, and this is actual change in function height. And then over here, this dy, this was our blue line. And this is change in tangent line height. And again, what I was saying is that this dy, which again is the change in height of the tangent line, is approximately equal to this delta y, which is the change in height of our function. So again, these are very similar to, right, linear approximation. Linear approximation is talking about the total height of the function. Differentials is talking about the change in height of a function. But either way, we can use the tangent line to approximate these things. All right, that is it for this video. Next time we'll go over a few more examples to really hit this home. Take a quick break, and I'll see you guys next time.